Bonjour tout le monde. Good morning or good afternoon or evening, depending on where you are. My name is Catherine Duclos, and on behalf of the Quebec Sleep Research Network and the Snooze team, I wanted to say thank you for joining us today. If it's your first time with us, welcome. So this is our second to last seminar today. But before we dive into the subject matter, I just wanted to give a brief overview of the Snooze Toolbox if you're new to this platform. So Snooze was really designed for individuals who don't have programming expertise. So clinicians, sleep researchers that want an accessible platform that doesn't require programming or use of command lines. But it's also flexible for people who want to develop their own tools and pipelines. So you can customize your tools, you can extend the pipelines if you need to, according to the studies you're running. And it's open source accessibility makes it designed for modern sleep science. You can save pipelines, they're reproducible, they can be shared easily. So it's really designed for optimal sleep research and clinical sleep medicine. So Snooze emerged from a highly interdisciplinary collaboration, bringing together sleep researchers, neuroscientists, engineers, developers, signal processing expert. So the development and ideation of Snooze was born from the vision and the leadership of Nadia Gosselin. So she's the one who initiated this platform, has overseen its development and its funding over the last several years. Senior sleep technologists Hélène Blais and Sonia Frenette have ensured that the platform remained grounded in real-world clinical and research workflows. Jean-Marc Lina and myself had been advising on tools to add to Snooze. And I also want to emphasize the central role of Karine Lacourse as the lead developer of the platform. So she was initially working with David Lévesque, but more recently has been working alongside Anye Bazregarzadeh and Mohamed Hassanazad as the core programming team. So the Snooze Toolbox is funded by several sources, including the American Academy of Sleep Medicine Foundation, the Brain Canada Foundation, la Fondation de l'Hôpital du Sacré-Cœur de Montréal, the Research Center at the CIUS du Nord de l'Île de Montréal, the Canada Research Chair on Sleep Disorders and Brain Health, held by Nadia Gosselin, and NSERC. So we are already on our fourth webinar this morning, which will be on EEG signals, from EEG signals to brain networks. So we're going to be talking about connectivity analysis and its implementation in Snooze. The presentation will be in English, but Q&A is in English or French. So feel free to ask your questions verbally at the end or write them in the chat box as we go along. Just a reminder, if you want to join us next week, Karine, Annie, and Mohamed will be talking about how to customize tools or develop on the back end of the platform. So it's more for developers or those interested in developing or customizing the Snooze platform. So you can go on Snooze Toolbox if you haven't downloaded the platform, or look at this scan this QR code if you want to access the website directly. Once again, thank you for joining us. So we're going to start with this morning's topic, which is connectivity analysis. So I'm an assistant professor in the departments of anesthesiology and neuroscience at the University of Montreal and researcher at the Center for Advanced Research in Sleep Medicine. And my lab's research really focuses on using EEG and brain connectivity analyses to better understand altered states of consciousness, ranging from physiological states such as sleep and dreaming, to pharmacologically induced states like anesthesia, and even pathological states such as coma and disorders of consciousness following a severe brain injury. So I'll be giving the overview and the introduction today. And then I will pass things over to Anye Bazregarzadeh. She has been a research assistant in my lab for the past 4 years. She holds a master's degree in electrical engineering from Shiraz University of Technology, where she developed EEG-based fatigue detection methods using convolutional neural networks. Over the past several years, Anya has worked extensively on EEG signal processing, brain connectivity, sleep disorders of consciousness, and has been really a key contributor to the Snooze project for the past year and a half. So after the introduction on connectivity analysis, Annie will take things over and show you how these tools are implemented directly in the Snooz platform. So today my goal is really to provide a practical introduction to EEG connectivity analysis. We'll cover what connectivity measures actually quantify, how connectivity networks are constructed, and we'll go through some basic graph theoretical approaches and a few examples of what connectivity analyses have taught us about sleep and how you can potentially apply them to your own work. So for decades, sleep EEG has focused primarily on activity, delta power, spindles, REM density, spectral analysis. But two brains can have identical power spectra, but radically different patterns of communication. So connectivity analysis emerged because researchers realized that understanding the brain actually requires understanding not only activity, but interaction. So today I'll show you how we go from EEG signals to quantifying how the brain organizes itself as a network. So EEG power tells us how active a given brain region is. In other words, it focuses on local activity under that electrode. The second level of functional connectivity, the second level is functional connectivity. So instead of asking how active a region is, we ask how two regions interact with one another. So connectivity captures pairwise relationships between brain regions, in this case, electrodes, as we see in the figure. And finally, using graph theory, we can go one step further. So rather than looking at individual connections, we can characterize the organization of the entire network. So in a sense, power tells us how active the brain is, connectivity tells us how brain regions communicate, and then graph theory tells us how the brain network is organized. And we're going to go through these different steps this morning. So when we talk about connectivity, there's several different concepts that are often grouped together. The first is structural connectivity, which we won't discuss today, but globally it refers to the physical wiring of the brain, the white matter pathways, for example, that connect different brain regions. So structural connectivity asks the question, who is connected to whom structurally? And the second is functional connectivity, which is the focus of most EEG studies to date. Functional connectivity doesn't require direct anatomical connection, but rather asks whether two regions show coordinated activity over time. So in other words, who interacts with whom? And finally, there's effective connectivity, which goes one step further. So it attempts to infer directionality or even influence. So rather than simply asking, are two regions interacting? It asks, which region influences whom? So functional connectivity can be divided into different families of metrics. One way regions can interact is through their amplitudes or their envelope. So even if signals are not perfectly synchronized, their envelopes can rise and fall together. And measures are referred to as amplitude coupling measures when they measure the degree to which fluctuations in the amplitude of two signals co-vary over time. So amplitude coupling essentially asks, do the oscillations get stronger and weaker together? And two examples of these measures are amplitude envelope correlation and orthogonalized amplitude envelope correlation. Phase coupling is another family that refers to the degree to which the instantaneous phases of two oscillatory signals are synchronized regardless of their amplitude. So the basic idea is simple. If two brain regions are communicating, then the timing of their oscillations may become coordinated, and we can quantify how stable that phase relationship is over time. So phase coupling asks, are the oscillations synchronized? And there are different measures you can use here also, like phase locking value, phase lag index, weighted phase lag index, debiased weighted phase lag index. So there have been improvements of these measures over time. There's another family of connectivity measures that operates more in the frequency domain and is based on the cross spectrum between two signals. So we can call it spectral connectivity. The term is not that widely used, but it's neither amplitude coupling nor phase coupling, but rather integrates both of these when it's measuring connectivity. So the first step is to decompose each EEG signal into its frequency components. Yes, so you decompose the signal into its frequency components. Both signals show a prominent oscillation around 10 hertz in this example. And then we can ask whether the activity of the two signals is coordinated in that frequency. So the coordination is quantified using the cross-spectral density, which captures both amplitude and phase relationships between the signals. So coherence and imaginary coherence are examples of such measures that integrate components of amplitude and phase while measuring the connection between two signals. So most functional connectivity measures tell us whether two signals are related, but they don't tell us anything about directionality. So directed connectivity is kind of this hybrid category between functional and effective connectivity. It attempts to estimate which signal constantly leads and which signal constantly follows. So one such example of this is the directed phase lag index. So it's based on the phase relationship between two signals. So in this example, signal A, you can see consistently precedes signal B, so that the interaction would be represented as A pointing towards B, meaning A leads B. B is lagging A. So this doesn't necessarily mean that A causes B. It just indicates that there's a consistent temporal asymmetry between the two signals. And then effective connectivity attempts to address the question, which region influences the other, by estimating the direction of information flow more specifically. So in this example, activity in signal A consistently precedes activity in signal B, but effective connectivity measures actually enable us to conclude that knowledge of A improves our ability to predict B. So as a result, activity of A helps predict future activity of B, suggesting really a directed influence from A to B, such that A causes B. And these metrics can include Granger causality, transfer entropy, dynamic causal modeling, as you see on the screen here. So once we have selected our connectivity measure and computed connectivity across all pairs of electrodes within our EEG, one challenge is to identifying which connections are actually meaningful. So some connections can arise simply because of shared spectral content, noise, random fluctuations. So to address this, we generate surrogate data sets that preserve the basic properties of the EEG signal while destroying the temporal relationship between two channels. So we're gonna shuffle the data in some way. And we then recompute connectivity many times to build a null distribution across these surrogate data sets. So the observed connectivity value that we obtain is then compared against this null distribution. And if our connectivity is stronger than expected by chance, for example, smaller than P is smaller than 0.05, then we keep the connection. Otherwise, we just disregard it. And this gives us a statistically filtered connectivity matrix and reduces the risk that subsequent graph metrics are driven by spurious edges or random noises. So after removing connections that are not statistically significant, we have our connectivity matrix. So each row and column corresponds to an EEG channel, a specific electrode, and each cell within the matrix actually contains information about the connection. So in this example on the left here, we have a weighted undirected network, and we can read it as such. C is connected to electrode F with a strength of 20. So we can see in the graph above that C and F are connected, and the line is thicker because that's the strongest connection within the network. So measures such as weighted phase lag index, coherence, imaginary coherence, amplitude envelope correlation can produce these undirected matrices. Measures such as DPLI or Granger causality or other effective connectivity measures actually produce these directed matrices So in this case, we can see the direction in addition to the strength of the connection. So here we could read that C leads F with a strength of 20, and we see this represented here with the arrow connecting C to F. To ease computational load, or simply to construct our network based on connections that exist, regardless of their strength, we can decide to binarize the threshold. So we can say any connection that is here, I keep, and all the other connections I erase from my network because they're not true connections. And here we have a resulting binarized network where we lose the weight of the connections, but we retain the structure of the connections. We can also decide to apply a specific threshold when we are binarizing and decide to keep only the top, 30% strongest connections. So in this case, I retain only connections that are above 10, and I remove other connections. So you can see that I kept this one here, which was a strength of 13. I kept this one, which was a strength of 15, and here that was a strength of 20. So this gives us an idea of the network constituted from the strongest connections, which is a different approach. But deciding on the threshold is certainly one of the challenges when applying connectivity analysis. And we can see that in the literature as well. There's the wide array of methods that have been applied. So if we keep every connection, the network can become very dense, difficult to interpret. But on the other hand, if we apply an arbitrary threshold, our results can depend heavily on where that threshold has been placed. So an alternative solution is the minimum spanning tree, or MST, which was proposed as a way to reduce this threshold selection bias. So the idea is illustrated here. So we start with the full weighted network, and we progressively remove the weakest connections. So as long as removing a connection doesn't disconnect the network, meaning that nodes become isolated and no longer connected, we continue to prune down. So eventually we reach the sparsest possible network that still connects all nodes, which we see here. So this final network contains exactly n-1 edges, where n is the number of nodes. So the minimally spanning tree, or MST, can be thought of as the backbone of the network. In other words, the strongest set of connections needed to maintain communication across the entire system. The main advantage of this approach is that every participant can end up with a network of identical density, which makes comparisons across individuals or sleep stages or patient groups technically more robust. So once we've computed our connectivity matrix, we can represent it as a network or graph. We can then map out how every node or EEG channel, in this case, is connected to one another. So in graph theory, the basic elements are the nodes and the edges. So in EEG, the nodes are represented here as the circles, and the edges represents the connectivity values between, or the connectivity, whether present or absent, between these nodes. One of the simplest properties of a node is its degree, denoted as K, which is simply the number of connections it has to other nodes. So we can see here a lot of these nodes have only 1 or 2 degrees, and there are few nodes within that network that actually have many connections. So this one has 6, this one has 7, and this one here has 8. So these highly connected nodes within the system actually represent the hubs. And in a complex network such as the brain, these hubs really play an important role in network communications. So hubs are those nodes that either have a high degree and or a high centrality. Centrality actually means that a lot of communication actually has to go through that node to go from one side of the network to another. So in this case, we have these provincial hubs in blue, which have high degree, but don't have high centrality. And in yellow, we have a connector hub, which has really high centrality, and it connects these different communities. So this is the structure that we see, as I mentioned, in complex networks as opposed to random networks. So in a random networks, nodes will have a similar number of connections to other nodes within the network. And then in complex scale-free networks, such as the awake brain, we have most nodes with few connections, but a few nodes with very many connections, which play more important role. So one consequence of this architecture is that networks can be surprisingly robust to random failures. So if we have a random network and we suppress one node, we can see that it actually wipes out part of the network. If we suppress another node, it actually wipes out an even bigger part. So it's not very robust to failure. But when we have a complex scale-free architecture such as this, nodes that are likely to be nodes that are wiped out are likely to be poorly connected. So the effect on robustness will be more minimal. So as you see, we remove this turquoise connection, it only removed part of the network. If we continue with another node, it wipes out another small part of the network. And even with this hub here, we wipe it out and we still maintain communication within that network. So the balance between robustness and vulnerability is a defining feature of many complex networks, and hubs, they support efficient communication, but they also represent points of vulnerability within the network. So when we apply graph theoretical analysis to characterize our network, we have various sets of measures that we can apply. One of the simplest questions we can ask is, how easily can information travel across the network? So the shortest path length is the minimum number of steps required to get from one node to another. So in this network here, we see that node I can reach node J in only a few steps, 4 steps to be more precise. And in this next network, which is random, we can see that node I and J, which have the same location, actually require 8 steps to get from one to the other because of the way that the network is structured. So global efficiency is the measure that actually summarizes this concept across the entire network. So networks with shorter path lengths have higher efficiency and are generally considered more integrated because information can flow more easily within that network. We also have clustering, which we also call clustering coefficient, and it asks a different question. So instead of looking across the whole network, it focuses on a node's local neighbors. So specifically, it measures how interconnected a node's neighbors are. So node A in this example has 3 neighbors, but these neighbors are not connected to one another, which results in a clustering coefficient of 0. In contrast, many of node B's neighbors are actually connected to each other, which results in higher clustering. So high clustering is generally interpreted as local specialization or local information processing. We also have modularity and participation coefficient that can quantify this kind of local versus global functioning. So modularity moves from local neighborhoods to the organization of the entire network. It quantifies the extent to which the network can be divided into distinct communities, which we also call modules. So a highly modular network contains groups of nodes that are strongly connected internally, but relatively weakly connected to other groups. This is often interpreted as a network that is segregated, where information will tend to remain within these specialized subnetworks. And on a nodal level, we have the participation coefficient. So a node may have many connections, but are those connections confined to one module, or are they more distributed across multiple modules? So this is what the participation coefficient will capture. High participation coefficient identifies connector hubs, so these nodes that facilitate communication between otherwise segregated subnetworks. And finally, small worldness is a measure that combines 2 properties that we've just discussed. First, high clustering, which supports local processing, and second is short path lengths, which support global communication. So a small world network achieves both simultaneously. It sits between these extremes of balancing segregation and integration, and is right in the middle here between what we call an ordered network and what we call a random network. So this was an example of various graph theoretical measures that we can use to characterize our brain network once we've built our connectivity matrix. So let's bring everything together. So the first step is the usual EEG preprocessing. Then we will technically filter our data into a specific frequency band to calculate connectivity analysis. Most literature using connectivity measures actually looks at connectivity within specific frequency bands. Next, we select which connectivity measure we want to apply. So this is arguably one of the most important methodological decisions because different measures answer different questions. WPLI captures phase synchronization, amplitude envelope correlation captures amplitude coupling, DPLI captures directionality. So once you've selected and applied your connectivity measure, you then compare to the null distribution of your surrogate data sets to retain only the significant connections. And then you have your connectivity matrix. You can decide to apply a threshold. Is it a fixed threshold? Is it the minimally spanning tree? Do you binarize your network? Once you've made all these decisions, then you have your network and you can calculate various network properties using graph theoretical approaches. So finally, these these metrics are often compared against random networks or once again, surrogate data sets to determine whether the observed organization is meaningful and statistically significant. So similar to what we did with our connectivity matrix, we can build surrogate graphs and then see if our measures calculated within our network are actually statistically distinct from those of random graphs. So it's a lot of methodological steps to get to, what do we do with these? How do we apply these tools and what can they tell us? So if we start with a simple question, what happens to the brain or brain connectivity when consciousness is reversibly lost? And I have a few slides on anesthesia because anesthesia is a controlled, reversible suspension of consciousness. So in this study here, 9 healthy participants progressed from wakefulness to light sedation to deep unconsciousness under anesthesia for several hours. And we applied amplitude envelope correlation and weighted phase lag index to see how connectivity changed across states. So even on the right hand here, you can see that at the matrix level, we already see that connectivity patterns reorganize as consciousness is lost and then partially recovered. But what's most important from this slide, I think, is that even though these matrices are derived from the same recording, the resulting connectivity matrices look strikingly different when you compare AEC to WPLI. And that's because each metric captures a different aspect of interregional communication. AEC quantifies signal amplitude, WPLI quantifies phase synchronization. So we see that we can draw different conclusions depending on the methods we've applied. One of the reasons why directed connectivity measures are valuable is that they allow us to move beyond the question of whether two regions interact and to ask, in which directions do they interact, or even if we go into effective connectivity, who is influencing whom. So here in this example, the directed phase lag index, or DPLI, was used to estimate the predominant direction of information lead-lag relationships between brain regions. And we can see that when we're awake and conscious, we have a feedback dominant connectivity that is actually neutralized or reversed under anesthesia. This has been replicated with various agents such as propofol, ketamine, sevoflurane, isoflurane. So this is one of the properties that we see changing when we lose consciousness under anesthesia, is a change in the direction of that connectivity. This loss of feedback dominant connectivity has been proposed as one of the key network signatures of unconsciousness, and it aligns with theories emphasizing the importance of top-down information integration for conscious experience. So graph theoretical analyses tell a very consistent story as well. So if we look at transitions from consciousness to anesthetic-induced unconsciousness, we can also see that when we look at path length, it increases in unconscious states. Clustering also increases, modularity tends to increase, and global efficiency tends to decrease. So in other words, the network shifts from a globally integrated architecture toward a more fragmented and segregated configuration. And if we look at hubs, we also see significant changes. During wakefulness, hubs are located in the back regions of the brain. Under anesthesia, it becomes the frontal regions that are acting as our network hubs. So taken together, connectivity and graph theory, they reveal that anesthetic-induced unconsciousness isn't simply reduced to brain activity. It comes with a profound reorganization of how different brain regions communicate. So now, just to end on sleep before handing it over to Annie, connectivity has started to be applied, of course, to sleep data. This study was an interesting one, even though it was done in only 4 healthy subjects. It investigated whether phase locking value could be used to characterize and actually classify sleep stages. So the authors found that connectivity patterns differed substantially across sleep stages and different frequency bands, and that alpha band connectivity emerged as the most informative for distinguishing REM from N2 and N3. And by combining connectivity features across multiple frequency bands, they achieved sleep staging accuracies of about 96%, which actually outperformed many previous approaches based on traditional EEG spectral features. But connectivity is not only sensitive to vigilance state, it's also sensitive to individual characteristics. So this sleep study examined connectivity in a large sample of over 170 healthy adults ranging from, I think, 17 to 70 years old, using the weighted phase lag index, so WPLI. And the first major finding was that connectivity is not static across the lifespan. So theta and beta band connectivity tended to increase with age, whereas non-REM sigma band connectivity decreased. The topographic maps on the right here show where those age-related changes occur within the network. And finally, the second finding was a robust sex effect. So connectivity patterns were actually very different between males and females, with higher values in males, particularly in the sigma and beta frequency ranges. So again, the effects depend on sleep stage and frequency band, which goes to show that age and sex are major determinants of sleep functional connectivity. So if you want to use connectivity as a biomarker of sleep health, cognition, psychiatric disorders, we need ideally to have also age and sex adjusted normative values. We recently conducted a study at the Center for Advanced Research in Sleep Medicine. So actually data was acquired by Nadia and her team over 12 years ago. And Maya, who was a master's student in my team, analyzed the data to try to understand how sleep can progressively restore the functional network. So we analyzed 256 channel PSG recordings that were obtained from 16 healthy adults. We extracted the first and last episodes of each sleep stage, as well as pre and post sleep wakefulness. So this really enabled us to examine both differences between sleep stages occurring across successive cycles, but also to see how sleep progressively may have changed the functional network. So for each recording, we computed functional connectivity networks. We derived graph theoretical measures such as clustering, modularity, and global efficiency. So when we move from individual connections to whole network properties, clear differences emerge between sleep stages. So here in this figure, we have the first in light blue and the last episode in dark blue of each stage. But if you look at light blue and dark blue together, comparing sleep stages across them, one another, you can see that non-REM sleep is characterized by higher clustering and higher modularity. So we have more local segregation. And REM sleep actually shows the opposite pattern. So we have lower clustering, lower modularity, and higher global efficiency during REM. This suggests that information can travel more easily across distant regions of the network during REM sleep. And, it makes sense because REM is also the stage most strongly associated with vivid dream experiences, making this network organization more aligned with wakefulness than with non-REM sleep. Now, if we shift and we look at the difference between the first and last episode, and we look specifically at wakefulness pre and post sleep, we actually see that sleep seems to reduce modularity, clustering, and to increase global efficiency. So our period of wakefulness following the episode of sleep is actually more efficient. So this answers the question, does the architecture of the brain network change from the beginning to the end of the night? Well, the answer seems to suggest that yes, in this preliminary data. So key takeaways before Anya takes over. Connectivity analyses are powerful, but the results are only as meaningful as the methodological choices that you will make along the way. So it reveals interactions, not just activity, which is relevant to provide insight into large-scale network organization. But there are many decisions that you need to make. Which frequency band are you filtering in? Which connectivity metric are you applying? Are you thresholding? Which thresholding method are you used? Are you constructing a weighted network, a binarized network? So these choices will lead to different conclusions. And then we saw that connectivity is sensitive to physiology. So there are changes in connectivity across sleep stage, but also across age, sex, vigilance state, etc. And there's not a single best connectivity measure. There's no one right way or wrong way to do things. You have to choose the method that best matches your scientific question, which is always the hardest part of your scientific process. So I'll stop here and let Anya share her screen for section 2.
So thank you, Catherine. Hello, everyone, and thank you for joining us today. I will start with section number 2, EEG inspection and cleaning. So in this section, I'll briefly introduce the EEG inspector tool integrated in Snooz, which was developed to support visual inspection and pre-processing before performing connectivity analysis. So before performing any connectivity analysis, EEG quality is extremely important. For example, muscle artifact can increase the phase synchronization and provide misleading information. And that's one of the main reasons we have integrated EEG inspector in Snooz to provide an interactive pre-processing step before running any connectivity analysis. So the workflow starts by loading the data. Right now, it supports EDF, natus, and SLR recordings. Then users can select non-brain channels like ECG, EOG, and EMG, and then inspect the channels and mark the channels that are fully contaminated by artifact, and then segment the signal into epochs and mark noisy epochs, and then after all, check the quality of the signal and to see if they're happy with the quality of the overall signal, save the annotation for further analysis. Right now, I will briefly show how this workflow looks inside the Snooz. So the Inspect EEG channels is available under the Pre-Processing tab in the Snooz. After loading the data, users can interactively inspect the EEG signals and non-brain and identify non-brain before proceeding to the next step. So here are all, in this slide, are all the steps that the users should take to save the annotation for the EEG inspector. In the first screenshot top left, users can visually inspect the EEG recording and identify noisy channels. The bad channels are marked in red and can then be excluded from further analysis in the Snooz. And the top right is screenshot artifact epoch rejection. The signal has been segmented into epoch based on the recording length, and the user can visually reject the epochs that are fully contaminated by artifact or excessive noise. And finally, after visual inspection, user can review the PSD of the clean signal to evaluate the overall signal quality before saving the annotation to accessory file. And once the data has been visually inspected in clean, the annotation generated by EEG inspector can directly be used in the analysis workflow inside the Snooz, and this helps that connectivity estimate are compute on cleaner and more reliable EEG signals. So in this section, I will introduce the EEG connectivity analysis tool available in Snooz, and the goal of this tool is to help researchers study functional communication between different brain regions using EEG signal. And I will first present where the tool is located inside the Snooz, and briefly explain the theoretical background behind the implemented connectivity measures, like what Catherine mentioned before. And then I will walk through the main processing steps and analysis option available to the user. So the Analyze EEG Connectivity tool is available under the processing tab in Snooz. In the current release, the tool supports two connectivity measures: a weighted phase lag index or WPLI and directed phase lag index or DPLI. The WPLI is based on the method proposed by Wink in 2011, and the DPLI implementation follows the approach described by Stam in 2012. And after connectivity computation, Snooz applies an additional statistical procedure to reduce the impact of chance-related connectivity. That's what Catherine mentioned, and this procedure is based on the method described by Duclos in 2023, and I will explain the statistical procedure and its importance in more details in the next slide. So in the second step of the tool, the user can exclude a specific annotation or events from the analysis. For example, the artifact that has been previously detected using the EEG inspector can automatically removed from the analysis pipeline. And in this example, channel artifacts, non-brain segments, and noisy epoch identified by EEG inspector are excluded. And the next step allows the user to configure signal filtering according to the research question. Users can select their desired frequency range directly in the filter settings signal. And the user can also define the recording scope for the analysis. For a sleep recording, connectivity can be computed within a specific sleep stage or a specific annotation. And the unscored option is available to the users who are not working with the sleep data, and which allows them to trim the signal into desired duration. So in this step, users can select the connectivity metric to compute either WPLI or DPLI and defines the epoch length used for the analysis. So this step is important because it determines how the signal is segmented in time. Shorter epochs provides better time resolution but can be noisier, while longer epochs gives more stable estimates but reduce the temporal details. And also the overlap affect how smooth the resulting time course is. Like more overlaps give smoother results over time, but the estimates become more similar to each other. And once the data is segmented, Snooz computes the connectivity for each epoch and for each pair of channels. For each of these pairs, the connectivity is compared against the surrogate distribution, as Catherine mentioned, and these surrogates are created by disrupting the temporal structure of the signal and preserve the signal properties but breaks the true phase relationship, and this gives an estimate of what connectivity would look like under the null hypothesis of no real interaction. And to check the significance, a non-parametric statistical test is applied between the observed value and the surrogate distribution, and this p-value here is used to threshold for rejecting a chance-like phase coupling. And the number of surrogates control how stable the null distribution is. More surrogates leads more reliable statistical estimates, but increase the computation time. So users can select the surrogate number of surrogates based on the time that they want to spend to compute connectivity. And in this section, I will present the output generated by the connectivity analysis tool in Snooz. So at the final step, Snooz summarizes generated output and save them automatically after the analysis is complete. The first output is the connectivity matrix in TSV format, where each value represents the connectivity strength between a pair of channels. For DPLI, connectivity values range between 0 and 1, where larger values indicate stronger phase synchronization. And for DPLI, values range between 0 and 1 again, but the interpretation is directional. So a value above 0.5 indicates that one channel tends to lead another channel in phase, and the value below 0.5 indicates the opposite direction. So this is the first output, and the second output is a heat map representation of the connectivity metrics, and this provide a fast visual overview of connectivity strength patterns across all EG channels. And the third output is the head connectivity plot, which visualize channels interaction directly on a head shape layout. For WPLI, the connectivity is undirected, so the edge intensity reflects the connection strength. But for DPLI, the visualization represent directionality, so that user could observe leading and lagging relationship between brain region and the head shape layout. The only point about the head shape layout is that it only generated when the number of channel is enough to plot the head shape layout. So in the future work, we will beyond the classical phase-based connectivity, we will also include other types of connectivity, such as amplitude envelope correlation, which was explained in the introduction. And this allows us to capture slower fluctuation and gives us a more comprehensive view of functional interaction. We will also implement the graph theoretical brain network analysis, where we can characterize how the brain is organized as a network. We will look at the global properties like characteristic path length, global efficiency that reflects how efficiency information integrated across the brain, and we also look at the local properties such as clustering coefficient and local efficiency that describe how strongly neighboring regions interact, and finally describe the overall organization of the network using measures like modularity and small wordness. And also we have planned to implement the brain signal complexity, which gives us information about how rich and unpredictable EG signals are over time, and chaoticity-based measures that capture the nonlinear and dynamic features of the brain. And these measures can help us understand different brain states in a more fundamental way. And some of these measures has been implemented in Snooz, but it's not available in this release. But it will be. It could be used. It could be. If someone requested, we can provide the measures for them. And here are the Snooz references. And thank you for your attention. And please let us know if you have any question.
Thank you, Hani. As you can see, this is just the beginning. So there's a lot of things we can do and a lot of directions in which we can take these tools in. Anya has worked very hard to start implementing some of the connectivity measures we use in our lab, but then again, if you have special requests as to the metrics you'd like to see implemented beyond what Anya has already shown, feel free to let us know. So thank you again. Merci tout le monde.